Yay.
Thank you for that. Let me give you a bit of background about myself to start with. I first became licensed in Australia in 1963, and I had at that time a limited license because I was not interested in the HF bands anymore, having spent quite a few years as a shortwave listener, and I was interested in the frontiers. So that was above 30 megs. And I studied radio communications engineering at the Royal Melbourne Institute of Technology, which is now a university. And I subsequently joined the Australian Antarctic Division in 1969 and spent a year at Casey Station in Antarctica, returning in 1971. Following which, I secured a job with the Ionospheric Prediction Service, now known as Space Weather Services, and spent nearly 8 years there, working on transequatorial propagation research and ionosondes, ionospheric sounders, and then subsequently left for a job as a journalist. So and I've been on and off the bands over the years. I spent a lot of time on 6 meters. Owing to my interest in VHF propagation, which I was involved with while I worked for the Ionospheric Prediction Service, I maintained my contacts with the scientific crew that I worked with. So in recent years, I've returned to, well, since the early 2000s, I've returned to researching and writing and about propagation, in particular about VHF propagation, and playing on the bands right up in the microwave region.
Are you changing slides, by the way, Roger?
Sorry?
All we're seeing is the start slide. Are you changing slides?
Start slide. Yes. Okay, coming up.
There we go.
Factors influencing F-layer propagation at 50 megs as solar cycle 25 peaks. So let me give you a roadmap about what I'm talking about. Firstly, I'll begin with all life on 6 meters begins with our sun. And I'll move on to surprises of the solar cycles, the sun's influence on our ionosphere. Winter is not always discontenting. Mindfulness, path elevation and antennas. The importance of azimuth. Opportunities from precursors. And are we there yet? Well, this is from the solar influences. Observatory in Belgium, which has been recording solar factors and indexes since before we were all born. So here's where we have been since before 1960. And everybody recognises the big cycle peak down there at 1957-58. So what's the trend here? This looks very odd because ups and downs and all the rest of it. Solar cycle 24 was very disappointing. So the trend looks distinctly downwards. But is that so? When we look at what's happened over recent years, since solar cycle 24. We went through a minimum. At the minimum, the sunspot number, the smooth sunspot number, the very smooth graph line there, at the end of 2019, it was a value of 1.8. But now it's, well, the smooth sunspot number back to 6 months ago is around 140, 150. That's yet to be basically decided, but it's very spiky. You see it's all over the place. So it's been up above 250. The yellow one is sort of like the daily, and the monthly is the sharp up and peaks, and the smooth ones there is the straight lines, or the smooth line, I should say. And the dashed lines give you two views of a prediction or a forecast. In 2024, the estimated sunspot number May to October ranged between 149.1 to 159.1, so about 150 to 160. That's the smooth numbers. The observed sunspot numbers are exceeding forecasts regularly, like this. This one's from NASA ISES Center. So you look at the chart there, that's it gives you a better view of the slide before. The red line was the original forecast made in 2019, 2020. And the range of the forecast is the pink band. And of course, we're well above it, which is where all the fun is happening at the moment. It's why all the fun is happening at the moment. So comparing solar cycle 24 with 25 so far, we have a look at this. This gives you a clear view, just like the previous one. So the final smooth numbers are always like 6 months ago. So this takes it over the cycle of months since solar minimum. Typically, the climb from solar minimum to maximum is around between 4.8 and 5.4 years, or sorry, 6.4 years. So it's climbed pretty fast, and it looks like it. We don't know whether it's going to top yet or not. We'll find out a bit more later. So the smooth sunspot number path is well above that for solar cycle 24, just to rub it in. So what's happening up there? Circulation in the ionosphere. See this rather complex diagram that has been simplified. So we have the Earth there. We're looking at the dark blue line in the lower part, labelled the magnetic equator, right, which is rather different to the equatorial equator, or the Earth's equator. Solar radiation comes in on the sun's side, of course, and generates a thermal tide. In other words, it heats up and expands the ionosphere on that side. And you get a tide, just like we get a tide in the ocean, which is from the moon. But the sun's influence here is on the thermal tide. And that moves away from the sun, northwards, southwards, and east and west. Solar radiation drives the global thermal tide. And that's a daily thing. which is why we get diurnal changes in propagation. Thermospheric winds from polar cap processes excite planetary waves. Now, the ionosphere is in what's called the thermosphere, which is where the Earth's higher temperatures, once we get up to beyond 100 kilometres, up to 500 odd kilometres, etc., the temperature rises from there. So that's the thermosphere. And in the polar cap, you get winds there which buffet the flow of atmosphere, including ionosphere. And so you get these periodic waves in temperature, pressure, and speed of the winds. And they settle on periods of 2 to 16 days. And they're related to the equinoxes. You get gravity or buoyancy waves, which arise from atmospheric shocks and ripples that join the mix. So this is sudden changes in winds for one reason or another. The ionosphere is blowing in the wind. So season is a factor. And our friend is the winter anomaly. And it looks like this. This is a basically a propagation prediction for June 2000, back in 2021, just to illustrate the reason that, illustrate the phenomenon. So, as you can see in the panel there, it's the F2 layer MUF, USA East Coast, East to West Coast, I should say. So at a sunspot number of 100, the red curve gives you this big bump through the winter months. But when it's lower than that, it doesn't look good. So in these years where we're above a sunspot number of 100, we can look to, or you can look to, propagation, F2 propagation above 50 megs for a few months of the year. And that sort of like applies across the northern hemisphere at about your geomagnetic latitudes. Oh, solar activity is obviously a factor because that prediction was based on the sunspot number, of course. So when it's up to levels you get occasionally at the moment, you get a much longer period between November right through to April. As we see here with the dashed line. Now, that's for a 4,000 kilometre path, which is of course, a really, that's sort of the generalised peak distance for F2 propagation at typical heights of 250, 280 kilometres, etc. So note the angle there. The propagation, the azimuthal angle is between 0 and 2 degrees. So here, the scales that I have exaggerated for the purpose of illustration. So more about the winter anomaly. So the 4,000 kilometre path in mid-latitudes for the Northern Hemisphere. Ionospheric predictions, I might point out, are made for a 3,000 kilometre path. So a 4,000 kilometre path is a rarer event. Path elevations are tangential, pretty much less than 2 degrees, as I pointed out. The reason is why we get this anomaly during the winter months is because more oxygen relative to nitrogen in the F region is subject to seasonal circulation. So you get circulation in the ionosphere from that complex diagram a couple of slides ago. With sunspot numbers from 100 plus, 6 metre F2 may open, as I said, over autumn, winter, spring. So rather than being confined to winter, you get extensions before and afterwards. Of course, in the Northern Hemisphere, or in your country, North America, autumn is known as fall. So the mid-latitudes, the mid-latitudes are, transatlantic, Mediterranean, East Asian, Pacific paths. We'll see more about that in a moment. Let's have a look at the winter anomaly in the Southern Hemisphere. It sort of like flips the curve a bit. This is for sunspot number of about 180. So here it's occurring between March and August, where the dashed line shows. So that puts an overlap with the Northern Hemisphere. So we can get interhemispheric F2 propagation, which has been happening occasionally. The MUF in a 4,000 kilometre path, the mid-latitudes, Australasian and South Pacific regions, looks like that. So here, fall runs between March and May, and winter between June and August. We miss out on the spring months. There's only a small overlap, late March, early April. Again, scales have been exaggerated for the purpose of illustration. And tenor elevation angles are another factor, which I've been mentioning all the way through. Here's a couple of antenna azimuth measurements, estimations using EasyNet for a path between Peru and Australia, Sydney, the capital of New South Wales, which is about 800 kilometres south of here, where I am at the moment in Queensland, at Southport on the Gold Coast. So with a 3-element 6-metre Yagi 10 metres above the ground, diagram on the left, you get a peak gain at an elevation angle of about 8 degrees. It's for OA4TT over there down south of Lima, with a 8-element Yagi 20 metres above the ground. Is peak gain elevation is around 6 degrees. Not a great deal of difference, but it makes a difference on the underside of the lowest lobe, where you lose a bit of gain. So there, for OA4TT, the gain there, loss is about 6 dB, 6.5 dB. So 6-metre DX propagation paths are inherently low angle. Doesn't matter if it's F2 or sporadic E for that matter. Your antenna's working at the bottom of the first lobe. Now we need to know a bit about the equatorial ionospheric anomaly, because it allows us to cross the equator between the hemispheres in terms of propagation. This shows the peak ionospheric vertical frequencies north and south of the geomagnetic equator. from a technical paper I published back in the early 70s. So neatly, it can be symmetric, which allows for peak propagation, but sometimes it's a bit more lopsided than that. So the peaks you'll notice are around 20 degrees north and south of geomagnetic latitude from the geomagnetic equator. So ionisation builds up either side of the geomagnetic equator through a fountain effect. It's basically the solar radiation drives up ionisation, drives up electrons and ions from the very narrow band at the equator to very high in the ionosphere, and then gravity pulls them down north and south. So that's how you get those peaks. It's symmetrical at the equinoxes. So here's another view showing electron content curves. So the red areas are where it's peaking, where F2, or the vertical incidence frequency in the ionosphere, is at its highest in the red areas there, slowly declining either side, and east and west. You notice the extent east and west. This follows the sun eastward, but it maintains a quite high ionisation westward. Solar radiation and ionospheric convection maintain that latitudinal extent. Production of the equatorial anomaly, the EIA, follows the sun westward, as I said earlier. So, transequatorial propagation looks like this. Afternoon type transequatorial propagation, which most of you have undoubtedly heard about or even succeeded with. So it's based on the geomagnetic equator, or the magnetic dip equator. Much the same thing. The geomagnetic equator is a smooth version of the Earth's magnetic field. So you see the two equatorial anomalies there in the F layer. The transmitter on the southern side will be the ray path will be deflected across the equator without an intermediate ground reflection. And at different heights, you get different deflection, so you get focusing at the receive end, or at the opposite end. So this is afternoon type, or otherwise known as supermode TEP. It's a caudal hot propagation path with ray path focusing. So those north-south paths, strictly orthogonal to the geomagnetic equator, around 4,000 to 7,000 kilometres. But if it's oblique, you get it to 10,000 kilometres or more, 15,000, 16,000 kilometres. So here's here's an actual ray tracing path of measurements, based on measurements of the ionosphere along a longitude line, along the 150 degrees longitude line, actually. So this is between Seoul and Townsville in North Queensland, which is about 800 kilometres north of me. And this is a hand tracing that I've had copied from a fanfold printout from a printer, an IBM 360 back in the early 70s. So you see that the point where the magnetic equator is and the crests of the ionospheric anomaly. In this instance, about plus or minus 17 degrees geomagnetic latitude. So that's the real TEP path showing this focusing effect. Now, I've had personal experience of this with afternoon type TEP between Townsville and between stations in Townsville and in Japan. One afternoon, I was with one station, or with two stations living a block apart, about 30, 40 metres apart. And I could walk between the two stations. The most northern, they were more or less in a line north and south. So the northerly station could hear a signal, and it would peak S7 to S9. And the southerly station could barely hear the signal or not at all. And then I could walk as the signal began to fade at the northerly station. I could walk down to the southerly station and the signal would rise. So this is an extraordinary thing. Quite a wonder when you walk when you run across it. The footprint can be very small, which is why it seems to those of you who experienced it, it seems to be very spotty. So somebody in the next county won't hear a signal that you're getting at strength 9 or more, and they'll be furious, thinking something's wrong with the equipment. Anyway, so furthermore, so let's look at the Earth here, showing here we are. The Hawaii to Cook Islands is an orthogonal path, north-south, that's obvious, and the sort of oblique paths you get up and down the North America, right to the right to Central America. And note the dashed line is the Equatorial anomaly peak latitude, and the dark blue line, of course, is the geomagnetic equator. So let's look at longitudinal paths, taking advantage of the equatorial ionospheric anomaly and scooting along that path. So that's why you see sometimes Hawaii working into North America and into Japan. So a combination of the equatorial anomaly and the winter anomaly increase in propagation. The arrow, the slimmer red line between South America and Hawaii is a path that's often exploited. South America manages to get into the Asia Pacific region, as the lower red arrow shows. So that shows the east-west extent of exploiting the equatorial ionospheric anomaly. So let's do a bit of a summary. Our opportunities and experiences are controlled by the sun. Solar cycle 25 may be peaking or yet to do so. Winter winds are winners. Raypass elevation is smaller than you think. Azimuth matters more than elevation. Development of the EIA brings opportunities. The equinox is a good neighbour. Are precursors a factor? What do I mean by precursors? That is some event that happens at a lower frequency and earlier than when a path might open. So it gives you some idea. Now this is a bistatic, this is a recording from a bistatic backscatter radar run here. I made a mine, VK3OE, VK30ER. He has a transmitter at home and a receiver at a very auspicious location, 160 kilometres away. His articles on the construction of this and the use of it have been published in Dubis magazine, which back in 2012, 2014, for those of you who know the magazine. So from left to right, you can see the little bump at minus 92, yes, which is the direct signal. And the first F, backscatter reflection, is at minus 74. The second backscatter reflection at 4,800 kilometres away and spanning up to 5,000 kilometres is at peaks at minus 86. The first F layer around the world return signal at 42,000 kilometres is out there at the right, and it's only 12 dB below the first F backscatter skip, and backscatter signal, I should say. So this is a very interesting thing. You worked W3XS on 6 metres in Idaho when this radar trace was recorded. So how does this work as a precursor? You've got to get your signal into the F layer at a very low angle, coming up from a very low angle with the base of the ionosphere. So there's an exaggerated curves vertical view. Here's a more complicated view. You might launch a tangential ray there from the left-hand side, and you've got to get it deflected rather more, or rather, I should say, rather somewhat, so that it sort of just slides into the maximum of the F2 layer, a bit like a whispering gallery. The F1 layer deflects the ray path. It has to happen at critical angles, which means that the penetration frequency, FOF1, the vertical incidence frequency of the FOF1 layer must be, of the F1 layer must be between 4 and 5 megs and at a height around 90%. HF2 may do it. So this sort of gives you a view of around the world propagation characteristics. looking at the previous diagrams. So for a mid-solar cycle sunspot number of around 70, between 70 and 80, you get curves like this. And that gives you a probability of getting around the world propagation at different frequencies. You see it declines very sharply after 40 megs. As the sunspot number goes up, then those curves jump up by about the same as the grid distance, as the horizontal grid distance. So, primary factors when on the air. The solar flux index is your friend. SFI of 120 to 150 equals improving MUFs. SFI 150 to 200 equals excellent MUFs. We've seen a few of those over the last couple of months. 200 plus is pandemonium. Everybody for themselves. Keep a close watch on the A to K indices because that can upset things. Low values, quiet times, hunt and pounce. High values, you get geomagnetic storms. So return to your knitting. It trashes the ionosphere. 'Tis the flux what gives the pleasure, but the flare's what brings the pain, to paraphrase an old song. So, a future view. This is, NASA's solar cycle progression and forecast as of October last year. As you can see, the current cycle has exceeded expectations there on the left-hand side quite dramatically. So this is based on the solar flux, which is a better measure, in fact, of the connection between the sun and the solar activity and the ionospheric performance. Now that suggests that the next solar cycle, 26, might be at least the same as this one or higher. And there are lower prospects of it being lower. So, future view number 2. When we're looking at sunspot number, this gives you much the same analysis as the last one. So, it's certainly encouraging. Thank you.
Oh, that's great. Thank you so much. It really shows a lot of activity there. You're still sharing there. Maybe you can stop sharing now.
I'm trying to look for it. There we are.
There you go. We're back. Well, that's pretty good. And I'm sure some folks have maybe some questions there for you. So I'll let the gallery come up with some questions here. Who's got a question?
I've got one. Roger, fantastic presentation. Thank you very much for that.
Thank you.
The geomagnetic storms coming in and disturbing everything. What is the function of that? I've explained to my non-ham friends that it's like a high wind coming and you've got white caps up there when you want to have a smooth mirror-like finish, and now you've got ocean waves up in the ionosphere. Is that a correct statement, or is that kind of what's happening with a geomagnetic storm ruining everything temporarily?
Well, it's a it's a fair way to explain it. I wouldn't say it's analogous, but yes, it's a good way of explaining it to non-technical people.
So it's good enough for the non-hams.
Good enough for the hams too.
Yeah.
Because I got 3 cameras running out on where I live here on a dark island, and looking for meteors and aurora. And I notice when the aurora starts flying, then the bands go to pot. Although I do notice prior to the aurora coming up, the 6 meter gets quite good a day or two before the storm hits, it seems. Or is that just my imagination?
No, that is in fact true. Because the solar radiation and the solar wind improve conditions beforehand. It's the flares which bring the aurora, of course, because it's the protons and electrons that fired out from a flare. If it connects with, if it runs into us, or if we're in the way, then it flows into the ionosphere in the north and south poles. But that sort of jiggles the geomagnetic field, and that upsets the ionosphere quite substantially.
Thank you.
Any more questions?
Just an observation, when you mention 2 stations very close together, one getting into a DX station easily, and then one, what did you say, 50 meters apart? Or
Yes.
and they
That
weren't getting the
focus
propagation.
point. Yep, that focus point can be very narrow.
Interesting.
The same occurs on 6 meters. You get focusing on 6 meters as well. And of course the what comes out of that observation that I related is that the focal point moves. So the ionosphere is not, shall we say, fixed. Yeah, it rises and falls, and which is why partly why you get QSB, particularly with TEP, and so the ray path or the ray paths to and from your station wander over the ground somewhat. I back in the 70s when I was working in TEP research, I spoke to a scientist here in Brisbane, just to the north of me, who had during the 60s built a backscatter radar to study TEP, and this and other propagation. So this involved, of course, a rotating antenna, and then listening for the reflections, and the footprint looked like the footprint in the northern hemisphere looked like rather like the Nike whoosh. So it's this thin tick.
Interesting. Oh, you're muted, Paul.
Hit the wrong button. When you're, we see a lot of that in North America here, where we have these spotlights, as we call them, and I was operating in out of Denver, which And I was working certain stuff, but I was always having some problems not working the same stuff that the folks down in Texas and in Arizona and those guys were hearing a lot of stuff I wasn't. So I moved my station down about 125 miles and down to southeast Colorado, same state.
Paul has the luxury of 2 stations.
And all of a sudden, I'm hearing a whole bunch of stuff, and so I'm saying, "Hey guys, get on the air." ZLs are 5.9 plus. They're really booming in. And my friend up in Denver, Bill WT0DX, says, "Well, I can't hear them. You shouldn't get on the air and tell people this, Paul, because you're pissing everybody off." And I said, "Okay."
But Roger, you're saying that this focal point can drift around. So just because you're not getting it and he is, you should hang in there because it could drift over to you at any time, right?
Oh yes, yeah. That case that I illustrated with the antennas between OA4TT in Peru and VK2FLR in Sydney. The focal point of that began south of Sydney and steadily over the period of 90 minutes steadily went from south to north up to the Queensland border, up to this area, which was quite an astonishing thing. But that was sporadic E, not F2 or TEP. Some of the longer paths, you can get mixed mode propagations. So you get F2 and then TEP, etc. And you might get another lift from F2 or sporadic E at the other end. So really, really long, obscure paths are typically multi-mode.
Yeah, we've seen things like that, and it's been a crazy summer last year, and just as crazy fall. So
Yeah. Yeah. This winter is shaping up pretty wild too.
yeah, a lot of stuff going on east west, and I'm working guys, east coast, and then I got guys in Argentina calling me. So it's really odd, but we're happy with it because we can work more stations and more countries. And I'm just trying to figure out if I'm going to be alive 11 years from now to get that other big leap.
I was looking at your graph doing the same math, Paul.
Yeah, saying, okay, how old will I have to be?
Yeah.
Can I make it that far? Does it make sense, or should I just divest now? So anyway, thank you very much,
Back in,
Robert.
I'll just add one point. Back in the 80s, um, I wrote an article published in in a number of magazines, electronics and radio magazines. I wrote it with my previous boss when I worked at the Ionospheric prediction service, and Leo McNamara, non-ham but ham friendly. And we wrote this paper that said, "Kiss your last big sunspot maxima goodbye." And then Solar Cycle 21 came along and totally trashed that.
Roger, do you follow Scott McIntosh at all?
Yes.
He's got some amazing prediction system going, and we'll find out in 11 years whether it's 100% or not, eh, Paul?
Exactly.
Yeah, well, you see some of that now appearing in those two late diagrams from NASA. It rather more encouraging than discouraging, which is what they were previously.
Well, I think it was his second last or last presentation where he alluded to 26 being it's soon to tell. I mean, it's too soon to tell, but it's possibly a doozy because he goes by the length of the cycle, not the amplitude of the previous cycle, as being a better predictor of the next cycle. And if this one is shutting down early, which it might be, it's pointing to 26 of being a real doozy, is what he's saying. We can only hope and only try to stay healthy so that we're around for it.
Well, the current forecasts, it depends on who who you or which graph you want to look at. The space weather services here, say by September, we'll be back to what we were last July, I think, if I remember correctly. Whereas that the NASA one in my late slides there suggests that next January will be where we are now, with a hump in the middle.
Like a double peak
So
sort
it
of
looks
thing.
like, yeah, it looks like the let the good times roll.
Yeah, I'm for that.
Well, thank you very much for all your time there, Roger. And you're, into the next day. You're on Thursday now, and we're just finishing
Oh
up
yes,
Wednesday. So thank you very much. And that was very, very interesting. And hopefully you'll join the Front Range 6 meter group and give us your comments every so often, and listen to what we're doing up here.
yes. I found you on Facebook, not Facebook, YouTube.
YouTube, yeah, we're there a lot.
Yeah, I found that. So yeah, I'll keep an eye on that. If you want talks on similar related topics, as I said, I can talk to you about sporadic E at length. Really,
That would be a summer
a lot
conversation,
more
wouldn't
happens.
it?
No, summer and winter and odd occasions in between.
Okay.
And if you
Thank
had a
you,
bad
Roger.
6 meter season, it means somebody else had a good one.
All right.
Okay, thank you very much.
Thank you, Roger.
Thanks, Roger, for everything. Have a good day.
Bye.
Same to you.